Principal Deputy Assistant Secretary in the Office of Fossil Energy and Carbon Management at the U.S. Department of Energy, and is on leave as a Presidential Distinguished Professor of Chemical Engineering and Energy Policy at the University of Pennsylvania. In addition, as a Senior Fellow at the World Resources Institute, she led WRI's carbon removal program. Dr. Wilcox holds a PhD in chemical engineering and an MA in chemistry from the University of Arizona, as well as a BA in mathematics from Wellesley College. She has served on committees of the National Academy of Sciences and the American Physical Society to assess carbon capture methods and impacts on climate. As many of you know, she's the author of the first textbook on carbon capture, appropriately entitled Carbon Capture, published in March of 2012, and she co-edited the CDR primer on carbon dioxide removal in 2021. And with that, I would like to turn this over to Jennifer. Thank you for joining us again.
Great. Thank you so much, Will, and thanks for having me here today. Can you see my slides okay?
Yes.
Okay, great. So I'm going to talk about carbon removal, but I want to also just put it in a broader context. Some of you may not be aware that in the Office of Fossil Energy and Carbon Management, we did a reorganization of the office over the last year and a half or so. And part of that was adding two critical words to the title of our office. So carbon management, so it's fossil energy and carbon management. A lot of the investments that we have are really aligned with the climate goals of the administration. So for instance, 50% emissions reduction by 2030, emissions-free power sector by 2035, and net zero greenhouse gas emissions by mid-century. And when we look at our dependence across a lot of these different sectors that I'm showing on the right that are leading to the greenhouse gas emissions in the atmosphere, we recognize that some of these sectors are just hard to decarbonize. And so I'm going to talk a little bit, taking a step back of our office and what we're investing in, and then I'm going to take a deeper dive specifically into carbon dioxide removal and how we envision the role of helping us to be on a path to achieving net zero. So when we were going through the exercise of the reorganization of fossil energy and carbon management, first that we had to do is really look at and examine how we're dependent on fossil fuels today. And when you look at the different energy resources, natural gas, oil, and coal, you just recognize that our dependence on each of these is quite different. In terms of natural gas, I would say it's the most complicated because we use it today in a lot of different ways. We use it for commercial, residential, industrial heating. We use it for electric power generation. And then in certain cases, we could imagine that there are suitable replacements for natural gas, but in other cases, it could be difficult. So for instance, when you look at requiring high quality heat for the industrial sector, sometimes it's really difficult to think about appropriate replacements to the dependence that we have. And when you look at oil, for instance, our dependence is heavily on the transportation sector. And again, we have some good solutions. When we look at passenger vehicles and we look at all the legislation that's passed and the work that DOE is investing in terms of EV motors and batteries and making sure that we have an EV fleet for passenger vehicles and that we are really looking at electrifying the transportation sector, but parts of the transportation sector are very tricky. So for instance, when we look at aviation, long haul trucking and shipping. And so what our office is focusing on is can we do this in a way that's sustainable? Can we use CO2 as a chemical feedstock, react it with hydrogen to produce synthetic fuels or chemicals to be able to replace and squeeze the emissions that are associated with these sectors today. And also, if you're interested in learning more about our strategic vision, it's available online under the FECM.energy.gov website and under resources tab. And so just really briefly on the right-hand side, I'm showing a puzzle. And so what we're looking at is all of the pieces of the puzzle, and this isn't all inclusive, but just recognizing that there's no one piece that's going to get us there. That's going to get us to net zero greenhouse gases by mid-century. It's going to take a lot of different pieces where carbon management that encompasses a broad suite of approaches, but that's just one piece of the puzzle. And what we're also seeing here is the climate stripes. And so at that kind of reflection page or reflection in the page that in the middle, you see that we've gone from lower temperatures to increasing warming based upon our increasing emissions of greenhouse gases into the atmosphere. But the hope is that we reach net zero by mid-century. And if we invest today in scaling up approaches like carbon removal, like direct air capture, and we get it to the targets that we need to in order to be part of the solution that we're depending on it to be, so gigatons by mid-century, then you could imagine once we achieve net zero and we scale up this approach, that we might actually be able to start taking CO2 out of the accumulated pool of CO2 in the atmosphere. And I'm going to talk a little bit more about, just broadly speaking, carbon removal, and then a little bit on direct air capture too, and the work that we're investing in FECM. And so when you look at the two kind of primary R&D streams in our office, we're really investing in approaches that mitigate climate and environmental impacts of how fossil fuels are produced today. And that also includes legacy impacts. So recognizing, for instance, from coal mining, that there's legacy impacts to ecosystems and environments, such as ash impoundments from combustion of coal, such as acid mine drainage from mining, and also just stockpiled mine tailing waste. And so looking at ways to remediate those past and legacy impacts, and then in addition, making sure that as we use fossil fuels today across the different sectors that I just showed, that we have the technologies in place for industry to adopt such that we can avoid the emissions. And so in this is all of the carbon management work. It's point source carbon capture, it's tackling the accumulated pool in the atmosphere, but really in the near term to help us counterbalance truly hard to decarbonize sectors. It's a lot of these different pieces. Downstream management of CO2 and safe geologic storage deep underground. But just really a lot of different elements that we're looking at, recognizing the key pieces that at the end of the day, everybody needs to have access to energy, but that energy needs to be reliable, and it needs to be clean, and it needs to be affordable. And so really looking strategically and responsibly at the carbon management portfolio and the investments. Now, what I wanted to do too is kind of take a step back and look at comparing different streams that contain CO2 today. And so when we look at carbon capture, whether it's from a point source or directly from the atmosphere, you can do a back of the envelope calculation, which combines the first and second laws of thermodynamics to give you a minimum work estimate. And what that means is it's a rough idea of what the energy would be required in order to do the separation of CO2. And so when we look at more concentrated streams, in this case, I'm showing hydrogen from steam methane reforming. So it's a little more concentrated stream of CO2. And then you go down to more dilute systems, and cement and steel's on the low end here, but it can be as high as 25% concentration of CO2. Natural gas power plants are on the order of 3 to 5% CO2. Direct air capture is 100 times more dilute than that. And so when we look at these different concentrations, as we go from more concentrated to less concentrated, the more inert gas you have to process through your separation technology. So that's nitrogen, in essence. There's other things like water vapor and some oxygen, but mostly it's really separating CO2 from nitrogen. And the more dilute your system is, the more energy it's going to take to do the separation. And I'm going to come back to this next point again later, but also how pure are you taking the CO2? You're starting with a certain concentration. You also know the percent of CO2 that you want to separate out. A lot of times the direct air capture approaches are optimized to say 50 or 60% removal from initial streams. Point source capture is oftentimes, we're pushing the envelope of 95% plus percent capture. And then the other piece is like, how pure does the CO2 have to be ultimately? And it really, the answer is it's dependent upon what you do with the CO2. Do you have to put it in a pipeline or a truck or a barge to move it? Or can you use it on site? And how are you using it? And so I'm going to get back to that a little bit later, but these parameters, the percent of capture, the percent purity in the end, and that initial concentration really are all the driving pieces that allow you to do the estimate of what the energy is going to take to really separate. Now, not taking into account capital costs. So that's a different set of a different equation and a different kind of cost estimates. But this at least gives you an idea of what, for instance, the operating costs might be. On the left-hand side, what I'm showing is some of these different examples of where we can capture CO2 from point sources. And this is, again, just modeling, because we don't have these, a lot of these aren't demonstrated yet. For instance, in the infrastructure law funding, we're going to have 6 demonstrations, 4 associated with the power sector, 2 associated with industrial sector. And it's going to be really important for us to carry those out and demonstrate what the true costs of first-of-a-kind builds are. But if you can do you can do a model analysis to kind of get an estimate of what the nth of a kind cost is. And when you look at the nth of a kind cost for point source capture, you can see that it's just significantly less than saying taking CO2 directly out of the atmosphere, especially with the existing technologies today. And so really just wanted to drive the point home that direct air capture and other carbon removal approaches should not be seen as tools to offset emissions that we have the ability to avoid today. If you have industries that are retiring and can be replaced with renewables, if you have committed infrastructure associated with fossil that we are depending on to reliably provide power to communities that otherwise wouldn't have access, we have carbon capture technologies that we're investing in today. And so we need to be really thoughtful about carbon removal, the scale at which will be required, and really what is it really counterbalancing? And so in our strategic vision, we also went through this kind of bottom-up calculation and also looked at a lot of the different, broad portfolio of carbon removal approaches and how DOE is thinking about this in terms of investments across different parts of DOE. For instance, we have a lot of efforts, not just in FECM, but also in energy efficiency and renewable energy, the Office of Science, and also ARPA-E. We're all collectively investing in all of these different carbon removal approaches in the space. But when you do the bottom-up calculation and you ask yourself, what is truly hard to decarbonize today in terms of sectors? And when you do the math, and let's say that, we emit in the United States every year roughly 6 gigatons of CO2. When you look at the truly hard to decarbonize sectors like agriculture, long-haul trucking, aviation, and shipping, and some parts of the industrial sectors, and also parts of the supply chains, for instance, with methane emissions that are hard to avoid. When you add it all up, it adds to just over a gigaton of CO2. And so it's still on the order of gigatons. Maybe it's not, 5 or 10, but it's on the order of gigatons. And what are we at today? Today, we're at the order of thousands of tons of removal. And so somehow between 2000 and almost 23 and 2050, we need to be able to scale up. So in less than 30 years, 6 more zeros. From thousands of tons, we need to get to millions of tons. From millions of tons, we need to get to a gigaton. And that's because that's what we need for net zero. For the carbon we put out in the atmosphere, we've got to be able to take it back out for these hard to decarbonize sectors. And one could argue that the terrestrial biosphere, oceans, trees, take up roughly half of our anthropogenic emissions each year. But that comes at the expense of ocean acidification. And we're also seeing with increased warming that a lot of these sinks in terms of forests and land sinks that we depend on are reversing through forest fires, insect damage. And so we really don't want to depend on those natural systems behaving the way that they do today. We really want to make sure that we do 2 things in parallel. That's advancing deep decarbonization based on that puzzle that I showed earlier, but also scaling up carbon removal so that we have it when we need it in order to get to this scale for the truly hard to decarbonize sectors. And so, and I think it's a little bit more clear that these are just 2 different tools. Carbon management is a broad term that encompasses a lot of different things, but there's the technology that's much further along because we've got 20 years of investment at Department of Energy in really looking at capturing CO2, demonstrating technology at a point source so that you avoid its emissions ever entering the atmosphere. And so that's one tool. avoiding the emissions from entering the atmosphere, where the other one is taking it back out. And when you look here, just at these two cartoons, they look different. So these tools look different. When you look at a point source carbon capture plant, you really have these big absorption, scrubbing technologies and they can look different than this. They could also be solid sorbents, but the technology that's furthest along is looking at these solvents and these absorption columns. And when you look at a direct air capture contactor to capture the equivalent CO2, it takes much higher surface area and potentially a different land footprint, ultimately, different energy footprint, and maybe even different water requirements. And so we really need to be able to treat these as different tools, always prioritizing resources to avoid emissions in the first place, but recognizing in parallel, we need to also invest in scaling up direct air capture and carbon dioxide removal more broadly. In my introduction, we'll mention the carbon dioxide removal primer, the CDR primer. And so this is available online, open access. And just recently, we have actually, and the link is on the site for the open access book, but you can get hard copies now too. And so this is a great tool to just kind of get everybody up to speed, using the same language, using, a common kind of messaging and understanding of really what is it going to take for us to do this. And again, back to kind of the responsible way of thinking about it. And so what this is showing is really that bottom-up estimate of what are the hard to avoid emissions, what do they add up to, and how we need to decrease emissions rapidly, but combined with scaling up carbon removal. And so you probably also know there's a couple of resources through the National Academy of Sciences of Engineering and Medicine. The first one that was really associated with carbon removal came out in 2015, and I had the honor of being on the authorship of both of these reports. The one in 2015, when we all first met, this was a topic that was kind of under the umbrella of geoengineering. And so it was, carbon removal approaches were kind of lumped together with solar radiation management. And through this exercise, we thought really carefully about what we wanted to call both of these kind of streams of approaches, recognizing that they're really two different knobs to ultimately get to, to ultimately prevent further warming and ultimately reverse some of the impacts that we've had. One of those knobs is changing the reflectivity of the Earth. The other is taking CO2 back out of the air. And so we decided to actually, in the end, publish two reports. One that was specifically focused on the reflectivity. Termed climate intervention rather than geoengineering, to try and try to make some movement forward with not conflating that term with both of those elements, because they have different types of risks and look really different ultimately. So again, two different tools. Later, we had a follow-up study that was negative emissions technologies and reliable sequestration, very different. This was really a research agenda. So we took each of the technologies or approaches in the original report, and we actually looked at it in terms of what will it take in terms of federal investments, the government to invest in each of these across the entire range to get to the scale of gigatons that's going to be required for us to meet our climate goals. And the good news is that blueprint has served us really well. And so at DOE, and I started this position as a political appointee on January 20th in the new administration, and really excited that we have these resources available to help us to launch a lot of the initiatives that you've heard about. One is the carbon negative shot. And so we launched this at COP last year, and looking at really all the broad portfolio from coastal blue carbon to accelerated weathering of rocks, to increasing carbon stored in soils, improved forest management, direct air capture with minerals, chemicals, biomass conversion, all of it. And so really including all of these approaches. And the idea here is really it's about investing in the R&D, not the demonstration. The carbon negative shot is all about kind of low to middle TRL, investing in that's technological readiness level. And so investing in the lower to middle TRL to push these technologies along the pipeline such that they're ready for demonstration. Good news is, now we launched the carbon negative shot, but the good news is very shortly after this, the bipartisan infrastructure law was passed and came through. And that provided $3.5 billion for direct air capture hubs. And so what that meant is that as we are investing, and you look at this picture, the approaches that are direct air capture, now there's a bucket, now there's a whole new office, or a whole new undersecretary now of infrastructure at the Department of Energy that's been developed to help oversee large projects and really looking at demonstrating these first of a kind, expensive, costly first of a kind technologies. But the carbon negative shot was about, really getting all the carbon removal approaches up to the TRL such that they can be ready for pilot and demonstration. And a key piece to that, kind of leveling the playing field across all of these approaches, is how do we get all of them to be durable? Just as durable as we've kind of outlined, direct air capture coupled to, a class 6 well with geologic storage deep underground. How do we get everything to be able to show that kind of durability, or to take CO2 and turn it into a carbonate where it's really hard to take that CO2 back out? And so being able to really demonstrate and make sure that we have monitoring, reporting, and verification across all of these approaches so that we can actually demonstrate investments are additional and leading to carbon removal that will go to scale that we need it to, and that there's proper quantification to really standardize across these approaches the best we can, at least maybe bucket some of the approaches with the key metrics that are going to be required for the monitoring and the reporting and the verification. And the idea there is if we invest our annual appropriations collectively across DOE and our applied offices and RPE and the Office of Science, and we do this, that ultimately we're going to go from thousands up to millions of tons over the next decade. And we'll learn by doing, and we'll learn through all of those investments to ultimately get the cost down on average to just under $100 per ton, net metric ton, within a decade. And then again, thank goodness with the bipartisan infrastructure law, now we have a place for those technologies as they move up the TRL pipeline to go. And so that's kind of, the vision of what we see in this work. When we look at our annual appropriations in FECM and how we invest in the direct air capture space in particular, we're really looking at every, from the bottom and working with Office of Science and leveraging and collaborating from a materials perspective. And it's not just developing a material, but you've also got to think and ask, if I've got to get to scale, do I have a way to scale this material up? Does it depend on rare earth elements or critical minerals that might be limited in terms of, being available in the earth? And then ultimately those materials and their scale up, we have to think about systems in a structured way, in a systems way. It's not just developing a material, but then the question is, how does that material perform in a system, in an integrated system where we can start to measure things that ultimately, estimate what those costs are going to be? So for instance, what's the pressure drop in the system? What's the heat of regeneration or thermal energy required, or the electrons and the power that's required in the system. And then ultimately getting to demonstrations in the field and recognizing that these systems are outside, and that means that these systems need to be durable to the conditions of the atmosphere, of the air. If you're in an arid or a humid environment, how that impacts water use. If you're in a polluting environment, how you might need to actually scrub the air ahead of the CO2 capture system, which could be actually a co-benefit to communities. But really recognizing that where you site these systems are going to impact the performance of the systems. And so we might actually have a feedback as we start to do demonstrations. And then the feeds are the front-end engineering design studies, which are always the first step ahead of a demonstration or a pilot. And so being able to kind of do a feedback loop to be able to learn. And this is really the sequence of the investments that we're making in this space. Some of the specific technologies here, again, in terms of systems, thinking about these kind of more chemical engineering concepts that relate materials to process and, diffusion and chemical kinetics. It's not just about the reaction and how fast CO2 reacts with an amine or, a hydroxide or to form a carbonate, for instance. But it's also, are there diffusion kinetics? Does the CO2 have to move through a liquid? Does it have to, in order to get to where it's actually going to chemically bind? And so being able to estimate, for instance, those types of parameters will tell you oftentimes how big your system has to be, which then relates to the capital expense, the sizing versus the energy, and the pressure drop is more about, the thermal, and the power is more about the operating costs and the energy of the system. We've invested too in a number of pre-feeds that are, located in different regions across the United States so that we can be thinking about those different weather impacts on the approaches and the technologies. And this is just an example that I have here from the World Resources Institute that talks about a solvent-based approach where you're starting with a very, very strong base, potassium hydroxide, and recognizing that the amount of water that's lost through evaporation to the atmosphere depends on where you're siting the project, and also depends on what time of the year. And so just recognizing that these are systems that are outside and they're really, impacted by the natural environment. And then mentioning too that we have to be careful not to treat all direct air capture technologies the same. I often see, it's easy to fall into the trap of you take a number from the National Academy of Sciences, even though it's a range, and you take that energy and you say, okay, this is what's required to take 1 million tons. If I want to do a gigatons, I'm just going to multiply by 1,000. That's a lot. But, ultimately at the end of the day, each technology is, that's pretty unique. And sometimes you have a technology that requires high thermal heat or, high temperature heat, high quality heat, and other times it's lower. And so the energy needs are really different depending on the technology. The water needs are different depending on the technology. For solid sorbents, you have a weaker base that's a mean base, and you're not just separating CO2 out, but you're capturing water, and it could be a net producer of water. So it's really important to not treat all of the technologies the same. And there's not a silver bullet. Each one has a set of pros and cons. I think ultimately at the end of the day, it's going to take a portfolio, and all have a role to play. And along the lines of the energy piece, one of the efforts that we looked into is, what if we took existing utilities today? If you look at, for instance, geothermal and nuclear, and they're producing, power, but recognizing at a geothermal power plant that you have a working fluid that goes through a condensing unit to maximize efficiency of the power plant, and that working fluid after the condensing unit is injected back into the earth. Well, the condenser could be the direct air capture unit. And so if you have a solid sorbent that can go as low as, say, 80 degrees C, you could imagine the working fluid of a geothermal power plant going through the contactor and coming out cooler than it went in. And now you inject it back in, and you inject the working fluid back underground. In that case, you're not saying, do I produce power or do I do direct air capture? You're doing both. You're able to achieve both through that integrated system. With nuclear, oftentimes, these are built to operate 24/7, but the grid isn't always needing the electrons 24/7. So is there a way to couple to direct air capture? And in this case, it's nuclear, so you can take the high quality steam if you have access to that. And you could couple it to maybe, a solvent-based approach that has that stronger base. And that, now again, you're integrating systems and using your nuclear plant is still running 24/7, but when the electrons aren't going to the grid, you're maybe passing some of the steam to the direct air capture unit. So thinking about in a creative way
我正好
to
现在
bring
趁
down
它
the
热，我
capital
抓
expense, because now if you don't have to worry about how you're getting, building the energy plant to couple to direct air capture, it changes things. And so this past year, we were able to award $11 million for 4 FEED studies. Again, these are the first stage ahead of like a pilot or a demonstration, front-end engineering design. We had one that was coupled to nuclear direct air capture, and we have another, actually 2 that were nuclear, 1 geothermal, and another was looking at the waste heat from a steel plant. And so really just kind of creatively thinking about connecting direct air capture to existing utilities or residual heat from industrial processes. The other piece that's interesting here is that when we think about nuclear and we think about geothermal, we think, carbon-free power, which is like the goals that I outlined at the beginning, 100% by 2035. Well, in this case, when you couple to direct air capture, you don't just get carbon-free power, you get carbon-negative power. And in some regions, that could be quite powerful, especially when we think about those hard to decarbonize sectors like agriculture. Another little side story that I wanted to tell that I think is interesting, and I talked about it a little bit at the beginning, but that whole notion of like, we don't always have to think about taking the CO2 from very dilute air to 99% plus purity because we're going to move through a pipeline. Depends on how you use the CO2. So if the CO2 is used as a chemical feedstock, for instance, to combine with alkalinity to form a carbonate, like through mineralization, maybe you only need 15 or 30% CO2. If the CO2 is being fed to algae, and there's multiple uses downstream for how you use that algae, but maybe you only need 5 or 20% concentrated CO2. And I don't have it up here, but if CO2 is going to be chemically converted when combined with hydrogen, maybe even through electrolysis for synthetic fuels, one pathway to sustainable aviation fuels, again, how low can you go in terms of the CO2 concentration, without having to outsize your reactor? And that's an interesting question. And so when you look at these energy calculations, again, just the power of doing the back of the work envelope calculation with minimum work, you notice up for direct air capture, there's this little blue sliver. That means there's a parameter space in terms of energy that overlaps with the energy that's required to take CO2 out of a stream that's 100 times more concentrated. So CO2 from a natural gas-fired power plant, 100 times more concentrated than air. But there's a parameter space where the energies are equivalent. Direct air capture to that scenario. It's just a different way to think about it, because maybe you don't need to actually move the CO2 if you can use it on site. The beauty of direct air capture sometimes is that there is a flexibility in siting. Again, we have to go back to those regional considerations, those weather impacts on the system. But this is something that I hope, gets you thinking outside the box a little bit, because a lot of times I think direct air capture is just, each technology looks the same, and it's just not that way at all. I mentioned a little bit about the co-benefits piece. This again goes to siting and being thoughtful about that. This is just overlapping data that's publicly available of greenhouse gas emissions, ports based upon just, the volume of the goods that they handle each year, because ports are often known to be, polluting regions. And so the question is there an opportunity where we can co-locate a direct air capture plant with some of these areas? Again, thinking more about the areas where the emissions are hard to avoid, or there are even baseline emissions. And you could imagine that if you have the direct air capture process, you're not just, there is going to have to be some kind of air filtration process in order for the carbon capture to be effective. And so just thinking about this and siting is important. Wanted to just talk briefly too about the bipartisan infrastructure law funding. Again, I mentioned $3.5 billion for direct air capture, and also a prize competition that's $115 million. It's also important to recognize that we have a carbon utilization program So thinking flexibly in a flexible way about how to manage the CO2, whether it's taken from the atmosphere or from a point source. You could also imagine converting it to something that's useful. And the FEED studies on carbon capture technology, those are really associated with infrastructure, so moving the CO2 around. And then finally, just a little bit of an update on our direct air capture hubs. Can't say a whole lot. You all know that we issued a request for information way back almost a year ago. We also conducted a number of applicant education workshops, one virtual and several on site across the United States. We issued a notice of intent back in May, and then we have something kind of coming out. It says September there. We're in September now and getting to the end of the month, but it's coming soon, and we're really excited about that. And again, if you're interested in learning more, I urge you to download our strategic vision. And I also urge you to just go take a look at our website, because one of the things that we've got there too is all of our engagement guidelines. So like societal considerations and impacts, all of that is available on our website too. And so encourage you to take a look if you're interested in learning more. And with that, I'm happy to answer any questions.
All right. Thank you very much, Jennifer. So yes, let's go to questions, and I encourage everybody to populate either the chat or Q&A box beyond what we have now, and we'll proceed for the next few minutes. Let me start with a question. Do you see a major role for tribes in carbon removal, and what pathways are available in that context in the recent legislation in the United States?
Yeah, I mean, I think, in these early days, as we're just getting, funding opportunity announcements out the door, I think that, the parts to be thinking about is opportunities associated with geologic storage of CO2. And so those opportunities could be co-located with tribes. And then also, some of the carbon management work, if it makes sense, but it really comes down to what the communities are also interested in. So part of the engagement is being able to understand the concerns of a community. If concerns are around legacy impacts of the industry, if the concerns are around air pollution, jobs, every community and region will have a different sense of sensitivities and concerns. And so really that's the first step. I will say through the Loan Programs Office, there's also, like, not my office, different, but it's important to take a look, because I know that there's a lot of incentives, and I'm pretty sure, the tribes are there's added incentive associated with some of those loan program authorities. And so I would encourage, if there's an interest in that, to take a look. And Jigar Shah runs that program.
Okay, great. Thank you. Let's see. A question about Climeworks' method of direct air capture. And the questioner says the Climeworks method of DAC is just too costly. Your slide puts it at $600 per ton CO2 equivalent, with essentially free thermal energy for CO2 stripping in Iceland. I guess it's more of a comment, but do you have any thoughts in that context?
And I'm going to put some of these links, and there's the strategic vision, just to kind of get that one done.
Great.
Well, I mean, in terms of, Climeworks and some of the others, that are kind of coming out and being really public about their costs, are even higher than that. And I think the first of a kind, that's the point. That's why we need, the direct air capture hub funding for helping to pay for those first of a kind. And so one thing I'll say, a little detail, is that those demonstration scale projects through the infrastructure law, the government pays 50% of the capital, can pay up to 50% of the capital, not more than that. And the idea there is that, again, so we're looking at roughly 4 direct air capture hubs. And so getting those first 4 built out, with us helping at 50%, combined with the Inflation Reduction Act bumped up to $180 per ton, you know, it starts to make those first of a kind projects, they're doable. And so the key then is what can we learn from doing that? In the meantime, though, we have the carbon negative shot where we're investing in TRL that's before ready for demonstration today. And we've got to be investing, to be able to push more ideas through the pipeline. But those projects that are going to be demonstrated will come down in costs. And I can't speak for Climeworks, but I would urge those that are interested to just connect because a lot of, they're looking at learning curves and looking at, here's our first of a kind, here's how we went down, and here's how our third of a kind has gone down. And so every time we build, we learn something, and there's an opportunity gained. And so I think right now we've got these two critical pieces of legislation that are in place. We're paying 50% of the capital for the first of a kind, combined with the Inflation Reduction Act bump up. Number three, the third level is the voluntary market that exists for voluntary carbon removal. And we know they're willing to pay a lot, provided it's durable, So, I think we're in a really amazing time right now for impact.
Just a follow up on that, just to put you on the spot a little bit about prognostication. Where do you think the cost per ton of DAC may be in 2030 and 2035, for example?
Well, we need to be successful at our carbon negative shot, and so I think that if in 2035 we're able to hit the millions, not a million, but tens of millions of tons removal, I really hope we can get it down to 100.
Okay, great, thank you. Okay, next question. Somebody wants to know if you can share insights about how we can conduct monitoring, reporting, and verification in the context of direct air capture.
So for direct air capture today, I think, a lot of the approaches, like how we're envisioning it for like a 45Q tax credit, is really that it would be coupled to dedicated storage. And the thing about dedicated storage is that you have to get a Class 6 permit, and that's EPA. And the Class 6 permit requires monitoring, reporting, and verification. That's why we have an equation that works for direct air capture today. If the CO2 from direct air capture is mineralized into a rock, we don't have a good carbon accounting of that system. We need more life cycle assessment, more transparency in that. It would be wonderful to be able to have all of that framework out there so that then we can start imagining 45Q and more pathways being eligible. But today, kind of conventionally, like thinking about direct air capture with solid sorbents, where you're actually, or solvents, where you're actually producing that high stream of CO2 that I was talking about, and injecting it deep underground. When you're doing that, again, you need a Class 6 permit, and the Class 6 inherently has the MRV that's coupled to it. And this framework exists, and that's why we have a federal tax credit for direct air capture. But we need that same type of solid framework across all of our carbon removal approaches. And that's where our carbon negative shot is coming in. We had a workshop just this past couple weeks ago where we brought together a lot of the companies that are in this space that have already been kind of invested in, from a voluntary perspective. We brought the companies into the same room as our national labs to be able to strategically think about what are the tools that we have off the shelf, to make sure that the CO2 isn't re-released, to make sure we can quantify like baseline and additional carbon removal. And just to try to get some of these thoughts out there and doing a little bit of, matchmaking between the companies and the rigor of the national labs that has the expertise to do this quantification. and also just not an agenda, kind of like a third party of trying to set up what does the framework look like for each of these various approaches. And so just really getting started on that work.
Yeah, that's a good way of referencing the last panel today, which is going to focus on MRV in the ocean context, right? Which, if think about the concentric rings of MRV difficulties, may be one of the most daunting, but important. So thanks for highlighting that. Okay, next question is, how extensive are CO2 pipeline infrastructure needs to build out to the scale that's envisioned or anticipated?
So we have loan program authority to build out the pipelines, but it's not just about direct air capture. It's also servicing the demonstrations for, there's going to be the hydrogen hubs, which has at least one is going to be based on fossil. We have the 6 demonstrations. And so significantly more, of course, than we have today, but they're loans and it's a loan program. And so there's $2.5 billion associated with those loans. And then I mentioned the front-end engineering design studies for really front-end engineering design for the infrastructure build out. And it's not just for pipelines. And so we're really thinking broadly. We're thinking rail, we're thinking trucking in some cases, we're thinking shipping, barge. And so really thinking broadly about this. And for more details on that, though, in the strategic vision that I put the link in the chat, we have kind of 7 key priority areas in FECM, and one is transport and storage. And so you can get all those details in there. And one of the things, though, that I will tell you for detail is it's important to recognize, I didn't get a chance to talk about it, but we also have $2.5 billion for storage and validation. And that's to build out the capacity of geologic storage of CO2. And if we're capturing CO2, whether it's from the air or a point source, we're going to need a place to put it. And the beauty is that by building out the capacity, and we're hopeful, like each one has to have a capacity of 50 million tons, each of those sites that we're investing in across the United States for storage. And then we're hoping that the $2.5 billion translates to, at a minimum, of 60 million tons of CO2 per year injection. And so I think that probably is a more useful number, because what it means is the capacity is built out, and then it allows more flexibility in where you're siting nth of a kind direct air capture plants, because now you have a place to put the CO2.
Great, thank you. Next question, does your agency offer programs to conduct RD&D of ocean-based CDR?
We sure do, yeah. So again, that carbon negative shot is across all approaches, including oceans. And we have in our appropriations authority to invest in direct ocean capture. I know this is of interest to RPE as well. It's of interest to NOAA, other agencies. And so this is something that we're also not just in a silo in DOE, but also talking to our other agencies about this, because Will, you mentioned MRV. When it comes to oceans, we've got to be really thoughtful about this. And so I also just put in the chat all of our, the guardrails or really the guidelines associated with all of our justice and engagement work for projects. And I think one thing that's to keep in mind is for these projects and dollars going out the door, they come with strings attached. So it's very different administration than previously. And so societal considerations and impacts. And part of this includes a community benefits plan. It requires applicants to engage with communities. As I mentioned before, what are the concerns of the community? If a community is pushing back and does not want, these opportunities where the government is paying 50% of these first of a kind demonstrations, there is the ability to go somewhere where there is an interest in doing these projects. And so now this part, the societal considerations and impacts, is 20% of kind of the proposal overall, weight in terms of the proposal grading. And you might ask, well, wait a minute, how are applicants even suited to be able to write these components up? And so what we've done is develop a lot of detail here to help applicants getting a robust application together, how to write and consider these engagement plans, to how to include diversity, equity, and inclusion into their plans, workforce plans into their application. And so all these things are critically important, not just the technology.
Okay, great. We're at the hour. Do you have time for one more question?
I can do one more question.
Okay. So the question is about the DAC hubs, right? And it's got a lot of different components, but you can choose which ones you want to talk about. It's questions about the diversity of these hubs and engagement and collaboration with hydrogen hubs.
Yeah, so actually those aren't really questions I can answer. So I'm not allowed to go into too much of those kinds of details. Let's just say that things are coming out soon. And in terms of the engagement, I just put a link in, and that gives you all of the details you need. And I'm also going to do this because we are always looking for new people to bring in to FECM. And that link right there is a link to all of our job opportunities. So I'm just kind of being selfish here. You can imagine we all have a lot of work to do over here. So we really need technical expertise, especially in the space of societal considerations and impacts. And we're really trying to bring in good expertise in this space and helping us with the engagement work too.
Yeah, I think that's a good way to finish, and I'm really encouraged by that. Right? I mean, one of the critiques often of government programs, and one of the critiques of our community, is really kind of under emphasizing societal aspects, right? And they're just a critical role in this, and I'm glad that there's more than lip service, in my opinion, being devoted to that in terms of these programs. So I definitely encourage people that may have that kind of expertise to think about this as a really important form of government service at this point. So with that, I would like to thank you again, Jennifer, for joining us and helping us really understand what the terrain is looking like now and where we may be heading. So thank you again.
Thank you so much for having me. Have a great day, everybody.
Thank you. All right, so we are at a point where we are going to stretch our virtual legs for about 12 minutes, and we will reconvene at 1:15 Eastern Time. At that point, our panel will focus on emerging issues of federal law, including interstitial aspects of federal law where we may need to develop additional legislation and regulations and some thoughts about what that might look like. So I encourage you to come back in a few minutes. 1:15 promptly, we will start again. Thank you, everyone.